Welcome to the Explainer. Now, this one is especially for all you teachers and educators out there. We're going to dive into some fantastic research from Dr. Sudhindra S.G. to create a really clear explainer on the incredible journey of early computing. We're talking about the shift from machines that filled entire rooms to the powerful little devices we all carry around in our pockets.
So let's really dig into this question, right? How on earth did that happen? I mean, it's pretty much the central story of all modern technology. And to get to the answer, we've got to go back in time, to a point where the world was facing a totally new kind of problem.
You see, before you can get a solution like the computer, you need a problem that's big enough to demand it. And in the early 20th century, that problem was just a massive, overwhelming explosion of complexity and data on a scale nobody had ever seen before.
Just think about this number for a second. 70 million. That's how many people were mobilized during World War I. Imagine trying to manage the logistics of that. Tracking people, supplies, it created a mathematical challenge that was just completely unprecedented.
And if you think that's a huge number, well, it was only getting bigger. A few decades on, World War II involved over 100 million people. The need for faster, more powerful calculation for things like cracking codes or calculating artillery trajectories, it literally became a matter of national survival.
And this wasn't just about war. This data tidal wave was hitting everywhere. The world's population was skyrocketing. Global trade was connecting continents like never before. Airplanes were starting to cross oceans. And science? Science was tackling incredibly complex problems. Those old cabinet-sized mechanical calculators, they just couldn't keep up. The world desperately needed a bigger, better brain.
So the first attempt at building that brain was, well, it was giant. In 1944, a team from IBM and Harvard unveiled this machine called the Harvard Mark I, and it was a true mechanical behemoth.
I mean, just look at these numbers. They're staggering. We're talking 765,000 components, 500 miles of wire, all synchronized by this massive 50-foot-long shaft that was spun by an engine. But the really important number here, the one to focus on, is the last one, 3,500 mechanical relays. These were its switches, the heart of the machine, and as it turns out, they were also its biggest weakness.
So here's the crazy part. For all that metal, all that engineering, it was glacially slow. 6 seconds to do one multiplication problem? Your phone does billions in that time. But even worse than the speed was the reliability. Those mechanical relays, actual physical switches clicking open and closed, they just wore out constantly. So while it was this incredible achievement, it was also a dead end. The big takeaway is that mechanical computing had finally hit a wall.
And this is where we get a really fun story, a little piece of tech folklore. One day, the machine just stopped working. The team, which included the amazing computer pioneer Grace Hopper, went looking for the problem and found the culprit literally stuck in one of the relays, a moth. They actually taped it into their logbook and wrote that they were debugging the machine. And yep, the term stuck. We've been finding bugs in our tech ever since.
So the problem was staring them right in the face, moving parts. A mechanical switch is always going to be slow and it's always going to break. The solution had to be a switch with no moving parts at all. It had to be electronic, and this led them to the vacuum tube.
And this just perfectly illustrates the massive leap in thinking, right? Instead of a physical little arm moving back and forth to connect a circuit, a vacuum tube just uses a flow of electrons. No moving parts means no friction, no wear and tear. It could switch on and off thousands of times a second. So much faster and way more reliable than any mechanical relay.
And this new technology was immediately put to the ultimate test. During World War II, an amazing team of British code breakers at a place called Bletchley Park built Colossus. With 1,600 vacuum tubes, it helped them crack encrypted German messages, which gave the Allies a huge strategic advantage and proved, without a doubt, the incredible power of electronic computing.
After the war, a machine called ENIAC took things even further. It was the first electronic computer that you could program to solve all sorts of different problems. And it was a beast, capable of 5,000 additions per second. But it had this one major fatal flaw. It used thousands of fragile glass vacuum tubes that burned incredibly hot. It was a total maintenance nightmare. It would often only work for a few hours before another tube just gave out.
So the vacuum tube was a huge step forward, but it wasn't the final answer. They still needed a switch that was tiny, that ran cool, that was durable, and that was cheap. And then in 1947, a team at Bell Labs delivered an invention that would, well, it would change everything. Enter the transistor. And let me tell you, it was a total game changer. It basically took every single problem the vacuum tube had and solved it. It was tiny instead of big, it was made of solid material, not fragile glass, it was incredibly reliable, and it used so little power that it barely got warm. This was the key that unlocked the door to our entire modern electronic world.
And it didn't take long for its impact to be felt. Just a decade after it was invented, IBM released the first commercial computer built without a single vacuum tube. And because transistors were so small and efficient, computers could finally shrink from the size of a whole room down to the size of an office desk. Suddenly, the idea of a personal computer wasn't science fiction anymore.
You know, the invention of the transistor didn't just change the computer, it literally changed geography. It gave birth to a brand new industrial heartland, a place that would become famous for technological innovation.
It's like this incredible domino effect. One of the transistor's inventors, a guy named William Shockley, moved out to California to start a company. Then his best employees left to start their own, Fairchild Semiconductor. And then employees from Fairchild left to create companies like Intel. And because the core material used in these new transistors is silicon, the whole area south of San Francisco soon got a new nickname, Silicon Valley.
So when you step back and look at the whole picture, the progression is just mind-blowing. We went from these clunky, unreliable mechanical relays to hot, fragile vacuum tubes, and finally to the cool, tiny, solid-state transistor. Today, the transistors on a computer chip are so small you can't even see them. Thousands could fit across a single human hair. They are the invisible building blocks of our entire digital world.
So, we've answered the first question. How our computers got so small, so fast, and so powerful? We followed the incredible journey of the switch, from a moth-infested relay to a nanoscale transistor. But that just opens up the next, and maybe even more fascinating question. How do you arrange billions of these simple on-off switches to do everything from sending an email to exploring the cosmos? Well, that's a story for next time.